Now let's move on to another kind of interesting interpretation of integrals and look at the fundamental theorem of calculus from another interesting perspective. So imagine you are sitting in this y axis, okay, and you have this function f of x, and say this function function is defined over an interval that you call a to b. Then I know what is the interpretation of integrating a function from a to b, say f of t dt. Okay, f of t dt. By the way, when you are computing definite integrals, there is no what you call difference if you change the variable. In other words, if you are computing x square dx between 0 to 1, I know that its answer is going to be 1/3. But if I, for example, write say t square dt 0 to 1, okay, its answer would also be what do you call 1/3. Even you can take anything. You can take, okay, let's do the integral of w square with respect to d w. Still the answer would be what do you call 1/3. So in definite integral, the change of the variable does not change the value of the integral. It stays same actually. Okay, and don't get used to yourself by solving the integrals or doing any mathematics with in the terms of any particular random variable actually. Okay, I mean people are very much what do you call used to of writing say f of x dx from what do you call a to b, but if they will if they will see that, okay, I have p of some alpha and I'm integrating with respect to d alpha, where alpha goes from 0 to 5, we're gonna see this in a strange manner actually. Why? Because we are not used to of solving the integral or doing mathematics by using say alpha as the variable actually. So my point is this, that don't get used to of kind of one notation. Always try to get the essence of it. I mean, and this is something that I always say, if you want to test actually that whether your understanding is kind of well defined or not, one of the way to know it, that is it notation dependent actually. So if your understanding of some concept, mathematical notion, is notation dependent, that's a bit troublemaking thing actually. Okay, so in every single mathematical idea, we always try to make sense, or we should always try to make sense of the idea independent of the notation actually. So for writing integral, I am writing say f of x dx or f of t dt or f of z dz, doesn't matter actually. All they mean the same thing actually. Okay, and you should be able to learn the stuff in the same manner. Okay, so let's return back to the situation. I have a function, okay, and I know that if I integrate this function from b to a to b, I know that what it is actually. So it's the definite integral. Okay. Now, if I say now, okay, let's not integrate from a to b, but I want to integrate from say a to an arbitrary point x actually. Okay, so it's a generic point x. It could be this point, this point, this point. It could be any point actually. And I want to compute, the area under function, but only in this interval. Okay, so only in this interval. Then what we need to do? The idea is going to be saying that, okay, now let's integrate the function from what do you call a to x. Okay, a to x. Now I know that when I'm going to solve this function, because if this is continuous, this part is continuous as well, then I know that this integral is going to be what? So f of t is going to be, you know, so for this small f, we need to have the antiderivative, okay? And then in that antiderivative, we need to substitute a to x actually, and hence you're going to get what do you call f of x minus f of a, where x is an arbitrary point between a to x. So if you are integrating a function from a fixed point a to an arbitrary point x in the same interval, then the result is not going to be a number actually, but it's going to be a function of x. It's going to be a function of x. For example, okay? For example, if I say that, okay, I'm integrating t square from 0 to 1, I know with respect to dt, I know it's going to be 1/3. But if I am integrating t square from 0 to x actually, where x is, you know, some point in an interval where this function t square is continuous. It's continuous everywhere, so it's not an issue. You can choose x, anything. So what would be the integral now? So it's going to be t cube by 3 and substituting 0 to x. So by substituting x, you're going to get x cube by 3, and by substituting 0, you're going to get 0. So the output of such an integral in which one limit is variable is going to be a function of that variable actually. So I can say that this guy is going to be some function of x actually. Okay? It's going to be some function of x. Now the question is, what would be the interpretation of this function? So in other words, after calculating this integral, we're going to get a function of x. And we have given that function a name g of x. Now g of x is telling us what? So g of x is telling us, or giving us, the area under the curve f of t from the fixed point a, or the starting point a, up to the point, what do you call, x actually. So we are talking about this area. Okay, we are talking about this area. By the way, if I choose this point here, this area is going to be small. Okay, the area, so if I choose this point as x, then my, you know, area is going to be, what do you call, small area. So this part would not be included. But as I said, I can choose anything, you know, x to be anything actually. Okay, x to be anything. Now, if I choose x somewhere here, so since the interval is big, the area is going to be more big actually. Okay, so when you are, you know, keeping one variable limit, then the area covered by the function, okay, covered under the function f of t is also going to be variable actually, in which you can variate x at different places and you're going to get the different area. Okay. The fundamental question is, okay, question is there a relation between g and the integrand f actually? In other words, is there a relationship between f and g? We got one hint already actually of it, but I don't want to get into that again. Okay, so this is the question that I would like to entertain. So in order to know this question, let's do a little experiment. The experiment is this, that okay, g of x is representing, so as g of x is representing the all area under the curve, what do you call, f of x from the interval, in the interval a to x. The question is, what would be the interpretation of g of x plus h, by the way? So g of x plus h, where h is some quantity, is going to be really say for example, if this is x and this is say x plus h, the interpretation of g of x is going to be that it is the area, okay, area under the same curve f of x, but this times it is on the interval from a to x plus h actually. Okay, so on the interval a to x plus h, the whole area under x plus h is going to be, okay, so it's going to be all this area actually, including this chunk as well. Okay. Now, if I want to make sense of this small chunk, so what I need to do? So from this entire area, all this big area, if I subtract this area, I'm going to remain with this small area. So by the way, g of x plus h, if I subtract what you call g of x, okay, so I can say that I'm going to get this small, what do you call, area, okay, this area under the curve f of x in the interval x plus h actually. Now if you see carefully, I mean, if I approximate this area, okay, this area by, for example, you know, this rectangle, okay, so this rectangle, this is the original area, while this is really kind of an approximation. I can approximate this difference by the area of the rectangle. Now what would be the area of this rectangle? The area of this rectangle is going to be, say, width multiplied by the height, okay, width multiplied by the height. So if what is the width of it? The width is going to be, so this interval starts from x and ends at x plus h, so its width is h actually. So I can say it's going to be approximately h, okay, multiplied by, what you're going to say, what is the height of it actually. So either you can choose height to be f of x plus h, or you can choose height to be f of x actually. So let's say that the height of this interval, this rectangle is f of x. Then I'm going to say that h is the width of the rectangle and f of x is the height of the rectangle. So if you multiply them, this area, okay, which is this area, okay, it's not a rectangular area, is approximately same as, you know, what do you call h f of x actually, okay, you know, approximately equal to this simple area. Now I know that I can improve this approximation by doing what? By creating more and more rectangles, or by making, for example, this the width of the area smaller and smaller. In other words, the width of the rectangle is smaller and smaller. So I can do it. And how can I do it? And I can do it by taking, you know, this h goes to 0. In other words, the distance between these 2 points, if I make that distance, the width tend to 0, okay, this rectangle is going to, you know, what do you call, become smaller and smaller and smaller actually. Okay. So if in this equation, if I divide both sides by, say, h, okay, this is approximately still f of x. And then I can say that, okay, if I take, you know, in this expression, if I take limit h goes to 0, g of x plus h minus g of x divided by h, okay, is basically going to be exactly equal to f of x actually. Is going to be exactly equal to f of x. Now what is this? Okay. What is this? This is really the derivative of the g prime of the x, f of x. But what is the derivative? What is the function g? The function g is this variable area. So I can say that with this intuitive calculation, I can say that if I have this integral a to x, where x is a variable quantity, f of t dt. So if I have the area, okay, of f of t under f of t from the interval a to x, and if I consider a small chunk of this area, okay, if I consider the really small chunk of this area, then this small chunk of the area is going to be precisely, what do you call, f of x actually. Okay, f of x. Are you getting the point? So that's one way to make sense of it, that if you have such an integral in which one limit is variable, and if you differentiate the integral with respect to the same variable, then the outcome is going to be the integrand of the function actually. The outcome is going to be the integrand of the function, and we saw it that why this is true. That, okay, consider the area between, from a to x and a to x plus h, and consider their difference. The difference is going to be this. And then I can approximate this difference by a rectangular region, h times f of x. And if I make h smaller and smaller and smaller, okay, this f of x plus h will get closer and closer and closer to really what you call f of x actually. Okay? So, this is an interesting conclusion of differentiating an integral actually. You can also get this conclusion, so this is not something really strange actually, that why, if g is the integral, g prime of x is the integrand of the integral. This is not something which is strange actually, that the output of the integral, I know that the output of the integral is the antiderivative, and this shows that indeed g of x is the antiderivative of f of x actually, because when you are differentiating g, you are getting f of x. You can see it more explicitly in another way. I've described it before actually, that if you take, say, a to x, okay, so your g of x is a to x, what do you call, say, f of t dt, then by a fundamental theorem of calculus, if f is a constant function, this is going to be the antiderivative of the f evaluated at what do you call x minus the antiderivative of a f evaluated at a, where this f is the antiderivative of small f actually. So this means that the g of x is really f of x minus what do you call f of a. And if you differentiate now both sides, okay, with respect to x, so you're going to get d by dx of f of x minus f of a. But I know that f of x is really small f of x, and f of a, since a is a fixed, so f of a is a real number actually. So if you differentiate a number, you're going to get a 0, so you get again, what do you call, f of x actually. So it's not an strange fact, okay, that if you are integrating a function from a to some variable x, so one of the limit is variable, and then with respect to that variable you are trying to calculate the rate of change of the integral, how the area is changing when the small x is changing, area would change as the value, what do you call, f of x actually. Okay, so this is what really one of the description of it. Now, what are some of the benefits of having such kind of, what do you call, integrals? There are lots of benefit. Let's just discuss few. So let's just discuss few. So So if I, for example, so here, let's start with one simple example, that imagine I'm saying that my g of x is a to x f of t dt, okay, where a is a fixed number 1 and f of t is say t square. So we need to compute an explicit formula for g of x, and we need to compute the explicit formula for g prime of x. In other words, compute g of x, which is not difficult to do, and compute g prime of x actually. Okay. So g of x, we kind of already computed it, that if you have 1 to x and you have say t square dt, then I know that this is going to be, its antiderivative is going to be t cube over 3, and then evaluate this antiderivative at the limit from 1 to x actually, which is going to be x cube upon 3. So we substituted x limit first and then minus, what do you call, 1 upon 3. And then what would be the g prime of x? The g prime of x, which can be treated as the derivative of this integral, but this integral is a function of x, so you can derivate, what do you call, 1/3, and what do you get? So 1/3, the derivative of 1/3 is going to be 0, so this is going to be 3x squared, so you're going to get x squared. And you can see this is precisely f of x as the function, what do you call, f of t equal to t squared. So we saw that if you have this integral, you get, what do you call, antiderivative, and if you derivate this antiderivative, you recover the original function. So this statement looks a bit different, but it's not saying something new actually. Okay, so you are looking at the same picture, but from a different perspective actually. So if you remember, we can say that this is like summing up f's, or summing up the rates of the function, okay, where the rates of the functions are modeled by this f. And then now you are saying that, okay, I want to know that how these rates, or the sum of the rates, is changing actually. Okay? Or you can physically interpret this by some quantity and then consider the derivative of it actually. Okay? Then consider the derivative of it. You can let me do another interesting example. And then move to the next example. So now, instead of d by dx, say I have d by dx, and I want to integrate, what do you call, secant t dt, but this time from 1 to not x but x square actually. That's an interesting thing actually. That if you can put x square there, x there, then why you can't put x square there? Why you can't put x square there? So what we should do in this situation actually. So in this situation, when you have to integrate a function, but the limit is variable, not just a variable, but it's a function of variable actually, then what to do? Then our first task would be to convert this kind of a form where you have what do you call a function of variable, try to turn it into this kind of integral. Try to turn it into this kind of integral where you just have one variable. And how you're going to do it, we can do it, or you can always do this with the chain rule actually. Okay? Chain rule. So how are we going to do with the chain rule? Sorry, this is not even squared, this is x power 4, even worse. Okay? So chain rule is going to help. And how the chain rule is going to help? Take say u equal to x power 4. In other words, take this function and equate it with u. So when you're going to equate this with u, what you're going to get? So if I replace this with u, then this function 1 to x power 4 secant, okay, t dt will become the integral from 1 to u and secant t and dt. Okay, and now let's calculate this integral with respect to dx, and this is same as calculating the integral with respect to dx, but the trouble is that the limit depends on u, while the function to which with respect to we have derived is what do you call x actually, where the u is the function of x. So what should I do? So we will do the same thing that we did in, for example, our differentiation exercises, actually our differentiating problems that apply the chain rule. And how are you going to apply the chain rule? Okay, so let's calculate the derivative of this 1 of u with respect to of the secant t dt with respect to du, and say multiplied with du by dx. Okay, so you can roughly understand that I have kind of divided and multiplied by du actually, but it's not like that. I have applied the chain rule. Okay, now on this I can apply what do you call my result, that if you have what do you call if you have to derivative, okay, if you have to derivate an integral with respect to a variable x while the limit is also x, then the output of this is f of x actually. The integrand would be the output. So if I have a function secant t and I'm integrating derivating the integral of this from 1 to u with respect to du, so what should be the output? The output should be secant and the variable u multiplied by du by dx. And now what you can do, you can substitute the value of the u back actually. So when you're going to substitute the value of u back, what you're going to get? So the secant of u is x power 4. Okay, so this is x power 4, and what would be the du by dx? So if the u is x power 4, du by dx is going to be 4x cubed. So this is what really is the derivative of this integral. Okay, this is what the derivative of the integral. You can generalize this even up to any function actually. So x power 4 is just one function. So what if I have to integrate with respect to dx from a to some some function h of x of this f of t dt. Okay, so I have to integrate from a to some function h of x actually, okay, of this function f of t dt. So what you're going to do? The same, that okay, let u is h of x, then this d by dx will become an integral from a to u f of t dt, and then I can, on this integral, I can apply the chain rule du and du by dx. The integral of this with respect to du is going to be f of u times du by dx is going to be the derivative. Let's keep it du by dx and then substitute the value of u. So this is going to be f of g of x, f of not g of x but h of x times d h of x divided by dx. Okay, d h of x by dx. Now what will be